Now, the registers of an architecture are its most fundamental unit of memory storage. So registers are small memory storage areas built onto the processor. They're volatile memory, so when the power goes away, the register values go away. But they're actually built out of transistors on the actual silicon itself. So RV32I and 64I have 32 general purpose registers plus the program counter, which is not general purpose because it points at the next instruction execute, as we already mentioned before. We also mentioned that what sets RV32E aside from RV32I is that it's for embedded systems and it only has 16 general purpose registers instead of 32. Now, RISC-V has this notion of an X-lang as the length in bits for registers for a given ISA. So for RV32I, 32E, the X-lang is 32. So if you're compiling for those base ISAs, then these registers will all be 32 bits wide. If you're compiling for RV64I, the X-lang will be 64, and for RV128I, the X-lang is 128. So these represent the 32 general purpose registers, X0 to X31, and the one special purpose register, PC, for program counter. So they show it as X-lang bits with the 0th bit on the right and the X-lang minus 1th bit on the left. And so different, documentation, different spec sheets, different architectures will all show their bit ordering differently. So this is just so you know that they are using least significant bit to the right, most significant bit to the left. And they're defining it in terms of X-lang, which could be 32, 64, or 128, depending on the ISA. Now let's talk about ABI, the application binary interface, which defines how data structures or computational routines are accessed in machine code. What we're going to really care about from the ABI is how it defines things like calling C functions. So that's specifically called calling conventions. Additionally, we like the RISC-V ABI because it gives us alternative and usually more intuitive names for registers instead of just X0 through X31. So let's talk about ABI mnemonics, like Johnny Mnemonic. So the ABI mnemonic is the more human-friendly name for the different registers. So the X0 register has an ABI name of the 0 register. The X1 has a thing called RA, which stands for return address. X2, SP for stack pointer, and so forth. We'll talk about each of these more in a second, but this is the actual table from the documentation, which you would consult if you're trying to figure out, something says that it's S1, what is the actual register behind the scenes? So we're going to use this sort of coloring convention where if you see something in green, that means we're going to actually see it in this class. And if you see something in red, that means we're not going to see it in this class. So first of all, the X0 or 0 register. If you read from the X0 register, you're always going to get a 0. This is basically a register which is hard-coded to 0. Consequently, if you write to the X0 register, it doesn't do anything because the register is hard-coded to 0. It's always set to 0. And this is seen on, some other architectures besides RISC-V. This is in MIPS or Spark, for instance. X1 register is also known as RA, which stands for return address register. This is also called the link register on some other RISC-based architectures like ARM, for instance. So that RA is your link to the past. It's frequently used when you call a function, and then that RA, the return address, is the link to the past wherever you called from. How do you get back to where you came from? That's RA. As we'll see later, the instructions that actually call into functions don't require that you set the return address to RA. You could actually use other general purpose registers, but again, we're talking about ABI mnemonics, and these are basically the conventions that they expect executable code to follow, in this case for Linux systems. Or rather, I should perhaps say for ELF-based systems, ELF being the executable and linking format, which is used by Linux, but is also used by other Unix-type systems. X2 is the SP or stack pointer register, and this holds the address, which is a pointer. This holds the address for the top of the stack, and so it's basically pointing at the last memory on the stack that is in use, and we'll talk more about the stack later. Now X3, the GP or global pointer, is something we're not actually going to see in this class. I'm told, but have not actually confirmed, that on Linux it holds a pointer to the data section where globals are stored. I did a very quick and simple test where I made a global and I said, okay, compile this thing, use a global. Do I see it using the X3 or GP register? And I didn't. So that's, again, I haven't actually confirmed this. Perhaps in more complicated code, you will actually see this ABI convention being used. Perhaps GCC doesn't use it. I don't know for sure. I'm just reporting on what I've found it is ostensibly used for. Another mnemonic that we're not actually going to see in this class is X4 being used as TP or the thread pointer. And on Linux, this is supposed to hold a pointer to the thread local storage, but if you don't have a multi-threaded app, it'll just be used as a temporary register. Again, I didn't make an app that has thread local storage. That's sort of a special thing. We have all sort of non-threaded, very simple applications in this class. Though, of course, you can go off and try to experiment with that yourself and see if you can see the X4TP register being used for this purpose. Back to conventions, we will see X5 through X7 are also called T0 through T2. So this is temporary 0, temporary 1, temporary 2. And these are temporary registers, and they're caller saved. That document before this one would tell you whether or not things are supposed to be caller saved or callee saved. And we'll talk more about what it means to be caller or callee saved later on in the class when we talk about the calling conventions. But the basic point is temporary registers are treated as temporary. So if you're going to call a function, you should assume that the function you just called could smash these register values. And consequently, you, the caller, need to go ahead and save those before you call into a function if you need their values preserved across call. S0 and S1, the saved registers, are supposed to be callee saved registers. So as opposed to these caller saved, the callee saved means you can go ahead and put values into these and you can call a function and the callee should not smash them. If the callee needs to use them, it's the callee's responsibility to go ahead and save these registers. Now, one of those in particular actually has a third name. So X8 equal to S0 equal to FP, the frame pointer register. This is used to store pointer to the base of the current function's stack frame if frame pointers are used. So frame pointers are not required, but basically if the concept of frame pointers is being used in the compiled code, then essentially each function has what's called a frame of the stack that is for its storage of its data, and the frame pointer would point near that. It's not exactly pointing at the base of the stack on RISC-V, as we'll see later on in the class. Then X10 through X17 are the A0 through A7 arguments to functions. So you can actually see there are up to 8 possible arguments that can be passed in registers to a function that is being called. And then we have all of our extra ones. We've got X18 to X27, which is S2, callee saved registers, S2 to S11, and then we have some more temps, T3 to T6. And so you might be asking yourself, why do we have 2 disjoint regions for temporary registers and callee save registers? We've got T0 and T2 up here at X5 to X7, and then T3 to T6 at X28 to X21. Likewise, we've got these disjoint S0 and S1 and S2 to S11. So why are these disjoint? Well, the answer is RV32E. So we said RV32E is going to cut down from 32 general purpose registers to only 16 general purpose registers. So that would look a little something like this. Bam! Love it. Excellent animations, you know. Yeah, so basically RV32E lets you cut off all of those upper 16 registers, but still all of these conventions would apply. And this makes it so that you can still have temporary registers. Some of them are going to be used the same way in RV32E versus 32I, T0 through T2, S0 through S1. The arguments now get slashed down from A0 to A7. Now you can only have upwards of 6 arguments, A0 to A5, in an RV32E ABI-based compiled code. But still, for functions that don't take a lot of arguments, things are going to look basically all the same. So looking at that in a similar way, you know, RV32I has 32 general purpose registers, RV32E has only 16. And boom! Love that animation skills, you know. So yeah, basically you just cut it down, and again, the justification for that is that they said in small RV32I core designs, the upper 16 registers consume around 1/4 of the total area of the core, so the actual silicon fabrication space, physical space, and consequently the removal saves around 25% of the core area and reduction of core power. So you can save space and you can save power if you have an embedded system that doesn't need all that complexity, doesn't need all of those juggling of registers. It can basically, perhaps it'll use a little bit more, you know, at the upper end, perhaps it's going to use a little bit more assembly instructions if if really they can't juggle everything in the available registers, but that is probably going to be an acceptable trade-off for people who are trying to keep the power reduction small for something that needs to run a long time in an embedded system. So the final word about compilers is that compilers have their own biases created by the programmers who make the compilers. And so although, we have this notion of temporary registers, for instance, you'll see as you look at the code that GCC emits throughout the class. Granted, it is unoptimized code most of the time, but it really seems to prefer using the argument registers as temporary storage values rather than the temp ones. And that's just down to a GCCism. We could see different behaviors if we looked at a different compiler such as Clang. So I just want to say, don't treat the ABI rules like they're the absolute truth of how a compiler will or must behave, and that if you don't see things behaving exactly the way the ABI says, that there's something wrong or you're not understanding. It's just compiler makers will generally abide by the ABI, but in certain cases they will deviate slightly.